these bounds are two-sided. So you want to look at what is the expected value. One way, the other. Their bounds are a little bit different on each side. One bound, one side.
You're good.
That's great, but it's not required. It's great you've done this. That's what you should be doing if you're doing this. Kind of a way to check your code and also a way to check your values. Yeah, so I would try this online. See if like some things. So saying and see if there's anything else that they can apply. And it's a common enough problem that sometimes and the truth is that may not give you the best amount, but if it gives something fairly close. Yeah, but they might be like too conservative, so it's much better. I think you're being tighter. This will give
Go to Creator Studio. Go to live stream.
Hey everyone, so let's get started. To start, I just want to remind everyone that the homework is due on Wednesday. So just remind you that you have to turn it in through Canvas. One person has a problem with Canvas I still need to fix, so I'll do it as soon as I can after class. If not, let me know. And it's due at 2:45, so you have 15 minutes to get to class afterwards, right? So if you have a question, there's the office hour times are here. Michael moved his office hour locations. He's now on the 3rd floor. This is where a bunch of other TAs are. Fonz are still upstairs, but it's right up the stairs, close to where the other offices are, I think. Okay, so any questions about that? There's been some good questions on the discussion group. We try and answer them quickly. Yeah.
So for the last question or the last part of question 4,
yeah.
Do you want a formula or a specific number for some value of n? It says, how many calls does it take as a function of that?
Yeah, so I'm looking for something like a formula. Now, so if you're used to like asymptotic notation, that's probably like a useful thing to do. But I'm not looking for specific values. A good way to figure out a formula, if you're not sure how to do it, is to do it for a range of specific values and try and find the pattern. And then and for this, it should be fairly, you should be able to figure out what's going on. Yeah.
But if you do have a formula that would give you the expected number of runs per n, that's good enough, or did you want?
Yeah.
Okay.
Yeah. If you have a formula, that's great. Great. So let's see. So the other thing I want to talk before we get on with the lecture is the proposal. The proposal. The project proposal is due a week from today. Some people have posted things on the discussion group, that's great, to try and find partners. I just wanted to talk a little bit more, just for a few minutes, about what the proposal is about again, just to kind of help facilitate some questions, questions you might have. So the scale of the project does not need to be kind of huge, but you should have it should be something you should have fun with, hopefully. And so if you look, the grading again is broken into these various parts, and every part except for the final report, more or less, you just need to follow the instructions, okay? Follow instructions and you'll get the points. The final report, that's where if you did more, I'll give you more points than if you did less, right? Other things, it's hard to judge the quantity because there's so much varying degree of stuff, but by the final report there, and so, think about, there's the basics of what you need to do, and those I think will get roughly like an A- grade. And then if you go up above and beyond that, you'll go up to the A grade type thing. So if you just do what's in there, you'll do fine. But that's where if you kind of do something much beyond what is required, then you'll get it more. And I still haven't set the final deadline for the presentation. We'll figure this out at some point. It could be during the time of the final exam, or maybe some, or for the poster presentation. We'll figure that out later in the semester. If you have concerns about those dates, let me know ahead of time if they're a problem. Okay, so the scale of the project, it should scale with the size of the group. Almost all of you, if not just about all of you, a couple of you have sent me emails today. I haven't always gotten back to you yet. I will later tonight. But almost all of you will be in groups of 2 or 3. And so the scale of the 3-person project should be a little bit more. And a good way to think about it is you should be focusing on some technique from class that you're going to be using, or you're going to be extending. So the very simple and basic projects, and these are not always the most exciting ones, but people can take them pretty cool, is to take a few techniques from class and variants of them and compare them on some real data sets to experiment. And kind of the more people in the group, the more types of things, the more better comparison you have to do. But it could also be an extension, something that you come up with on your own, or something more advanced that is beyond kind of this more vanilla stuff that we'll walk through in much more detail, but something I'll kind of mention in class but won't have time to go into the full depth of. Those are other kind of good things to look at to build a project around. If you're still trying to come up with a topic, I want something that you're interested in. I don't want to tell you topics because then people all do the same thing and it'll be kind of boring and you won't get as much out of it. But if you still can't figure something out and you found a group but you're looking for a topic, a good thing is to look at some data sets. Here are some websites that I had aggregated a while back. I think they're all still updated, but there are lots of big data sets here you can browse. There are plenty of other places online that you can find interesting data sets. And you start with those and then do something think of something cool to do with them. If you're not sure what to do with the technique from class, that's tricky. Try and remember from the first lecture, trying to overview something. You don't have to have all the details at this point, but try and pick something you think will be interesting to analyze. Ask me if you have questions. I usually try and get back within a day, if not sooner, or come and meet me after class or in office hours. So what I absolutely need a week from today in the project proposal is who is in your group, kind of roughly what data do you plan to use. Not a lot of detail, that'll be in the next step, in the data collection report. What structure do you plan to mine, or what technique do you plan to use? These are the basic idea. You don't have to have a lot of details here. Why do you think this will be interesting, right? And what will I find interesting about it, right? If it's, you're welcome to do something that maybe someone's done before, but try and make it so it's more interesting. I'll probably give more grades on the final report if I find it interesting, right? I'll try and judge you on the merits of everything, but all equal, if I find it more interesting, I'll probably get a higher grade. So these don't need to be full in detail, but just a rough idea. And from experience where I've read through projects and seen projects for a few years now, I'll try and give some feedback on I think this will work, or I think you might run into a problem here or there, or you should tweak it in some way. I'll try and give some high-level view to help give you feedback. But probably most of the reports, generally, 2/3 of them just are great at this point, and I'll just kind of let you keep going with it. But always feel free to ask me if you want more questions or have something specific that you'd like to know about. All right, so any questions about this now? Okay, great. So feel free to talk to me more later. All right, so let's get on with the lecture. Good. So today we're going to be talking about a technique called min-hashing. Oh boy.
Swipe to the side to get back to your, or hit the Windows button. Go to desktop.
Okay, great, thanks. Desktop.
The second on the far left, the bubbles, yeah.
Great, okay, great, thanks. Hopefully, okay, good. Okay, great, thanks. Good, I'm still learning how to use this. This is the department. I'm going to get my own, hopefully by next week. And okay, great. But this is, I think if you want to use these things, these are the best way to write on a big screen like this. So, all right, so min-hashing is going to be a way is basically going to take some objects that are sets and turn them into some other objects which are vectors. Okay, so it's going to be and you know, anytime you do this transformation, or not anytime, but often, you're going to get some error in this process. But why is this going to be useful? Well, so we're going to kind of have 3 steps here. So the last lecture was on these k-grams, and basically this was taking these documents and turning these into sets, right? So that was kind of the point of this last lecture, where we could take a document and we could turn it into a set, right? Where it was and the set contained these k-grams, which were these. If it was a 3 gram of a words, it would contain all the sets of consecutive 3 words. Each of those was an object in the set. Okay, but again, it won't matter so much what the sets are. They're just, we can think of them as objects from some finite space, right? So it could be that we have a set could be 1, 2, and 7 as a subset of, say, 1, 2, up to, say, 100, something like that. But typically the k-grams, these sets are much bigger. Instead of 100, this is like a million or a few hundred million of all possible sets of words, of 3 words in a row. Okay? Min-hashing will be going from sets into vectors. And then the reason for this is then next lecture we'll be talking about locality-sensitive hashing. And so this will be doing 2 things. One, it's going to take this min-hashing and generalize it to other sorts of objects and other things other than sets that we can take as input. But in particularly, it will work with min-hashing. And then it will allow us to answer 2 questions. And And so the idea here is that we're going to have, let's say we start with some, say, x, which is going to be a large number of these sets, okay? And so then the first question is we're going to have some query object. This is a query, and what we want to say is Q in the set X? So we want to answer this quickly, right? So the first way we could do this would be just to check Q against every object in the set, every object in X. So each X, think of, remember going back to here, each X was one of these documents, like it's a web page, or it's an email, or it's another assignment that we've seen in the past that we're checking to see you have it copied from. And we want to check, is your assignment matches exactly one of these other assignments, right? So they're teachers, if they're teachers in like the English department, they have a history of all of these essays. For college admission essays, there's a big kind of pool somewhere of all these old college admission essays, and they can see if yours exactly matches someone else's or is very close to it. We want to do this quickly without comparing against every single one, because that's going to take a long time. The other thing to think about is, are any two, say Q and Q prime in X the same? Right. So are there any two objects in this set X which are kind of the same or very close to each other? Right. So maybe you've taken another essay or another homework and you've changed a few words, a few names of variables, but otherwise they're the same. Is this something we can somehow check? And so we want to do this quickly. Now, in this problem is even harder. This one we would need to have checked against every Q against every document in X. Here we need to check all pairs. So if this was of size n, this took linear time in the naive way. This took n squared time to check all pairs roughly. Right? So if we just have sets, there's no clear way how to do this. But if we'll convert them into these vectors, then we'll be able to use this LSH technique we'll learn on Wednesday, which will show us how to do that. So basically what we'll do today is we'll talk about how to essentially think of pre-processing these sets into these vectors, and then we'll use this as a representation. And then we can use it for these sorts of applications we'll talk about Wednesday. Okay? And so we've already done some sort of modeling and some sort of approximation to get into these sets. So a little bit more when we convert to these vectors, some error we get in the process shouldn't be so bad. Okay, so it's not going to be an exact, a one-to-one transfer. Like, we won't be able to go back. This will not be possible to go back to the sets from the vectors. But that's going to be fine. We're just going to want to answer these sorts of operations, some sort of distance operation. Again, we're going to look at the Jaccard similarity between two sets, say S1 and S2, and we're going to get something like an approximate Jaccard similarity on corresponding vector 1 and vector 2 that correspond with the sets, and we want these to be roughly the same. So it's going to be a randomized algorithm, and they're going to have the same expected value, it turns out. And that with some Chernoff-Hopting bounds we talked about a couple of weeks ago, then this will show us that it's going to give us a pretty good accuracy. Okay. So that's kind of the general plan today. The general plan is kind of this is what we're going to cover today. Okay, so now, but how I'm going to progress in doing this is we're going to generate, so if you think of a vector, so we're going to go from some set into this vector, we're going to call it V, and say V1, V2, Vk. These are going to be the elements, and what we're going to do is we're going to talk about most of the lecture just creating just one of these elements, and we're going to create all of them in a way that's IID, independently. So each of the elements are going to be created the same way independently, and we'll talk about creating one, and then I'll talk about how to do them quickly, do all of them. But they're essentially, you just do the same thing for each of the elements. Okay, so I'm just going to create one object of this vector, and then by the fact that we have k of them created independently, if each one works right on average, then if I do a lot of them, they're going to work even better on average, and with very close to the expected value. And we'll show the expected value matches. Okay, so I'll be more precise here, but this is kind of a preview, because sometimes kind of seeing how this all fits together will be kind of, it'll be easy to get lost if I don't give you this high-level view. Okay, so again, we're going to be talking about the Jaccard similarity. So let's review this again quickly. The Jaccard similarity between two sets. Again, remember, this is A intersection, the size of A intersection B over A union B. So if the sets, if it's A equals 1, 2, and B equals 2, 3, 4, then this is going to be equal to, let's put here, the intersection on top is just going to be 2. The size of that is 1, and the union on the bottom is 1, 2, 3, 4. And so overall, this is going to be equal to 1/4, right? Okay, so that's the Jaccard similarity we talked about last week, and that will be the similarity that we'll preserve between the sets, and we'll preserve this in the representation of the vectors. Okay, and so we're going to go through an example now where in particular, let me just get a new page here. We'll look at S1, S2, it's going to be just value 3, S3, 2, 3, 4, 6, and S4 is going to be 1, 4, 6. And I'll go through an example where I'll turn these into vectors, and I'll walk through how I do it, and then we'll, and actually I'm going to turn these sets into a single number. Okay, this is going to be the element of that vector. If you remember up here, I'm just going to do this for one element of the vector, and then I'll repeat that. So all I need to do is create a single number that represents each of the sets. Okay, so the way I'm going to do this is by doing so the first thing to realize is that there's a different way to represent these sets. So we talked about text and then into these k-grams as sets. We're going to go to vectors. But before that, we're going to go to a matrix representation. And this will be kind of sometimes convenient for how to think about how this works, or on why it's going to work. So let's say that the domain is only 1, 2, 3, 4, 5, 6. And so I have different sets, 1. Okay, and so now this matrix, which is going to be in here, is going to have 4 columns and 6 rows. I'm drawing this just as a chart, and what's going to be inside each element is going to be a 1 if the set contains that value, and a 0 otherwise. Okay, so this will be one way to think about it. Okay, and so now, in order to get kind of, I want to get kind of represent this as a single number. So now again, I think of this as a matrix. It's a chart, but you read it by rows and columns. It's a matrix. And so the thing about this is that this is a bad representation compactly because it's going to be mainly zeros, right? If you remember with the, so it's called very sparse if it's mainly zeros, because because most words, most k-grams are not going to be in most documents. So like the third column, or the second column for the second set only had one k-gram in it, meaning maybe it has a few, but there are lots of possible things that could be in here. So I won't actually use this representation to store it in the algorithm, but I will use it as a way to think about what's going on. Okay, so now to do min hashing, we're going to do this in a few, in a few steps. So the step one is going to be to permute the rows. Okay, so if you remember these elements, when it says 1 or it says 2, that's not really meaningful. It represents some k-gram, and I haven't told you which one, right? And I'm just representing this abstractly. But the ordering of these shouldn't matter. They're just sets, right? Sets don't have an ordering notion. So that means that I can reorder them, and I'm going to reorder them in some way that's random. Okay, so I'm going to randomly reorder these rows. And so, for instance, I could do 2, 5, 6, 1, 4, 3. Okay? And then if I look at the quantities here in this matrix, S1, S2, S3, S4, now it's just permuting the rows of the matrix. It's got kind of squished here. Let me. Okay, so it's going to be like this one's going to be 1 is in there, 5 is in there, 6 is not in there, 1 is in there, 0 is not, and 3 is not. This is 0, 0, 0, 0, 0, 1. This is 1. What is this? 0, 1, 0, 1, 1. This is 0. Catch me if I have any mistakes here. And all right, so I've randomly permuted these rows. Okay, so now, in order to get a value out of each of these, step 2, I'm going to take, for each set, find the row that is the first one. Okay, and I'm going to give it the corresponding value. Okay, so what's going to happen is that S1, and there's going to be this will be some sort of hash function, not a random hash function, but this will be some locality preserving hash function. So this hash from M1 is going to give me a value 2, and this is going to be the ith one, but we'll. Okay, so for M of S2, I'm going to get the value 3. For M of S3, I'm going to get the value 2 again. And for M of S4, I'm going to get the value 6. Okay, so the 2, I did a random permutation. S1, this is the first one. I go and see a value 2. For S2, this is the first one. I go and see a value 3. S3, first one, go see value 2. S4, first one, go and see value 6. Okay, so this is the value of this vector. This is the value I put in the first entry of the vector. Seems kind of weird, right? Yeah? Okay, so the next, okay, so, and then I'll just repeat this. I'll do a different random permutation for the next element of the vector, and do this again with a different random permutation. And I'm going to get different values here, right? And that's how I fill up the whole vector. Okay, but let's, before we kind of talk about that, let me state a property that my estimate of the Jaccard similarity, this is my first estimate with just one value. I'll put a 1 down here because I'm only going to use one entry of the vector. The first estimate between sets Si and Sj is going to be 1 if m of Si equals m of Sj, and 0 if they don't intersect. Okay? So think of this m as a hashing. I'm hashing onto a value. Okay, and if they fall in the same bucket, I'm going to say that they have a Jaccard similarity of 1, and if not, they have a Jaccard similarity of 0, right? So Jaccard similarity is usually between 0 and 1. The more similar they are, the larger the value, the less similar 0. And I'm saying it's either 0 or 1. I'm being very strict here, right? It's either you pass or you fail, right? So this is a very crude estimate, okay? But it's going to have the property that the expected value of the Jaccard similarity, the approximate one, is going to equal exactly the true Jaccard similarity. So it's going to have exactly the right expected value. So it's either 0 or 1, but there's some probability it's going to be 1, and all the rest of the probability it's going to be 0. Right? So so it turns out that the probability it's going to be 1 is going to be equal to the true Jaccard similarity. That will give me the right expected value. Does that make sense? If I say the probability that they fall in the same bucket is equal to the Jaccard similarity, then this will be true. Does everyone believe that? Is that? Because then to get the expected value, I say the probability is 1 times 1 plus the probability is 0 times 0. The probability of 0 times 0 is always 0, so it's just the probability is 1 times 1, and the 1 doesn't do anything, right? So I just need to show now that the probability that they hash together is exactly the Jaccard similarity. Okay, so before I talk about how to use this, let me try and prove this fact. Okay? So is everyone... so usually it's a good idea, just so you understand the proof. It won't be too hard. And maybe once you see it, it won't be too confusing. But before I do it, think to yourself, how would you show this? Why would this be true? Well, why not? Yeah, so, well, I could use one of these different hash functions, these different similarities, like the dice similarity instead. If I use that one, well, those don't give the same value. So why does this work for the Jaccard similarity and not the dice similarity? So it's something specific about how the Jaccard similarity works. There's a way to do a similar thing for the dice, but it's not quite as simple as this one. And this is commonly what people use in this setting. Okay, so let's again review the Jaccard similarity between these guys. Remember, this is equal to the intersection between Si intersection and Sj over the union between Si union Sj. And this denominator, it'll be useful to write this as Si intersection Sj plus Si symmetric difference Sj. Okay? So this is equal to the union, right? Remember, the symmetric difference is everything in the union except the intersection, so that works. Okay, so I'm going to show that this is equal to the probability that they hash together. Okay? Okay, so let's consider for all the objects. So let's look at some. Let's call x equals to Si union Sj. And so I'm going to break this into this into three parts. This is equal Si intersection Sj plus Si symmetric difference of Sj. Okay, and seem to have turned off. Let's see if I can turn touch off again. So it's going to be these two sets. But if I think of this, if I draw a picture here, this is Si, Sj, and it lives in this space here. Right, so the intersection is this part. We'll call this value A. The symmetric difference is here. We'll call this part B. And then everything else is out here. Okay? And we'll call this part C, and this is not part of X. Okay? So now let's think about what happens when I do a random permutation of all of this domain. So I'm going to do a random reordering of this domain. And then I'm going to look at the set X, and I'm going to see which object is going to come on the top. So I'm going to do a random reordering of this domain, and which object is going to come on the top. Right? So I'm going to get some ordering in these cells here. Okay? And so a lot of the cells in this ordering are going to be from the set C. Some of them are going to be from the so some of them are going to be from the symmetric difference, meaning that they're in object Si or Sj, but not in the intersection, right? And then the orange ones are going to be from the intersection. Okay? So now, if I look at of the ones, so now in order to get, so if this is the ordering, then in order to get these hash functions, I'm going to ignore all the green ones. All the green ones I'm not going to ignore because I look at the first non-zero. Because I look at the first non-zero in this ordering, the only one that matters is this red one. The green ones don't matter anymore, just the red and the orange ones, the ones from the set A and B. Okay, and so in this case, the first one in this ordering was a red one, but it could have been an orange one, right? But this was a random process. Okay, so if the first one in the ordering is a red one, are they going to have a Jaccard similarity estimate of 0 or 1? 0. And if it was an orange one, it would have been 1, correct? So I need to know the probability that the first object was an orange one. It was from the set A, or from the set of size A, not from the set of size B. And the probability of that is going to be the probability of Mi equals Mj is going to be equal to the size of A over A plus B. Right? So the number of objects that are in the intersection, because it's a random reordering of these, just the red and the orange objects, and if I have to pick one of them at random to be first. If I happen to pick an orange one from the intersection, I get from the intersection of the sets, I get that the hash functions are the same. If I pick one that's not, then it's going to be, then I'm going to get the hash functions are different. So now we just realized that this intersection here is exactly A is exactly the size of the intersection, and B is exactly the size of the symmetric difference. So the probability that they collide is exactly the Jaccard similarity. And that means I get the right expected value. Okay? So it's kind of a short, cute proof. Okay, so I've got this very simple estimate now. This very simple estimate for one value. So now I want to, every lecture I tell you, it's going to happen. Okay, so instead now I want to get a better estimate of the Jaccard similarity. So now I want to say that my Jaccard similarity with the vector of size k is going to be here, between two sets A and B is going to be the sum over I equals 1 to k of 1 if MIA equals MIB or 0 otherwise. And this is divided by k. So I'm going to take the average of these. Right? So if I take the average of a bunch of things with the right expected value, it still has the right expected value. And it turns out that this is exactly the property you need to plug into the Chernoff-Hofting boundary talked about. So you can say something like the probability that the Jaccard similarity between two sets A and B minus the Jaccard similarity with the approximate one between A and B, that this is less than some quantity epsilon. Epsilon is some error bound between 0 and 1. So say like 0.1, right? So think of this as 0.1. So I'd say that this is going to be less than 2 times, what's this? Minus 2 epsilon squared over k times this delta value, which we knew the random variable that we were taking the average of was between 0 and 1, so this was k times 1 squared. Okay, and so if you set, so if you want to get this to be small, as you get k larger, you want it to basically balance this epsilon. So if you set k equals to approximately 1 over 2 epsilon squared, and epsilon is like 0.1, so let's say about 200, then you're going to get roughly a constant probability of failure. So maybe, so probably what you want is probably around 1,000. You're going to get that the difference between the estimate and the true value is off by more than off by no more than 10%, right? So 1,000 for k is kind of a good guess, or maybe more, maybe 10,000. Okay, so you're thinking, okay, I'm turning a set, which in all my examples had like 3 or 4 values into it, into a vector of size 10,000, right? So that's effectively what I'm doing. And each of these things involve permuting this huge sparse matrix. So this seems like, okay, this is, could be a little bit wasteful. Right? So where this is useful and where this was developed was for the very early days of the search engine. This was like pre-Google. And they were trying to do things where they're trying to remove these duplicate web pages. And so this was the easiest way to do it. So instead of doing all pairs, they would instead spend time to pre-process each web page into a vector of integers of size 1,000 or 10,000, and then just compare these vectors. And as we'll see next lecture, we'll be able to sort through these very quickly. Okay, but we're going to pre-process the sets into these vectors, and the k-grams you would get with web pages if you had a small number of k-grams could be much larger than that. Think if this was for characters, you have many more than 10,000 characters on most web pages. Yeah?
When you randomly permute the rows, do you have to have a rule that says don't choose the same element as the first element the next time?
No. And in fact, you don't know. The random permutation is chosen without knowing the actual documents. That's fixed. So you don't know which ones are the first. And if you look back at the permutation in this example, if all of my documents look like document S2, right, then I have to go a ways in all these zeros before I hit the first one. And since these are going to be really sparse, most of the documents are going to hit something fairly different when they hit their first one. So I'm not even going to know which one is really the first. Yeah. And in fact, okay, the next thing I was going to talk about is this process of doing it, turning into a matrix and permuting it, is really slow and expensive. This is not how you want to do it. I just want to describe it this way to kind of give you some intuition of why this works, what's going on. There's a much cleaner way of doing this that's going to be much faster to do. Okay, so, before I go into that, one reason why it's useful to think about this permutation is all we're doing is we're using just the first one in here. But there's a lot more information. If 2 of these columns have the second element does not match with the first and the third one, that tells us something more. Instead of just looking at the first one, we can look at the top several of them. And this will give us a much kind of a richer hash function. And you can show similar approaches with this technique as well. And this has some slightly better properties. So a little bit more complicated, but in some cases, if you want to kind of supercharge an algorithm, this actually, looking at the top 5 or 10 is going to work better than just the top 1. And I gave a reference in the note to a paper that starts to talk about these, but it's a really technical paper. But that might be a cool thing to explore. One of the PhD students here kind of implemented this difference and said it was for his whatever application he was using it for some big data processing that he got a fairly sizable improvement using the top K. Okay, so the next thing to talk about is this is how to do this fast min hashing. Okay, so how would we create these vectors in a way that's faster? In fact, how would you do this random permutation of the matrix? What's the right way to do that? How would you? We talked about, there's a couple things that I talked about so far. You had some operations I asked you to analyze in the. Gosh, what's going on here?
When you click that, it opens that application window.
Yeah,
Say if you use your finger and you swipe from the left to the right, which gets you back to your desktop with your finger.
Okay, great, thanks.
Mm-hmm.
We talked about a couple operations. One is a rand bit. You can generate a random bit. This gives you a 0 or 1. But what's most common, what's fairly useful to use, and we'll mainly use this in class. So this will generate a random, essentially a random double or a random fractional value between 0 and 1. Okay, so internally, what the computer will do is it will generate a bunch of random bits, and then it will string them together as like the binary decimals or something like that. There's various other ways of doing this, but so it's generating random bits underneath it, but it'll give us a random value between 0 and 1. Okay, and so, but we need to do a permutation of the rows of this matrix. How do we do a random reordering of something? Yeah?
I mean, rather than actually changing the matrix, couldn't you just generate random row indices, like in a few random row indices in order that don't duplicate each other, and then just go to those rows in the original matrix, rather than actually, I mean, if that's the slow part.
Yeah, so you could generate these random row indices. Now, so it's an interesting idea. There's kind of an issue with this, in that the rows are going to be really sparse. So what's going to happen is I'm going to generate this random row, and then probably it's going to be like, think of this as a 4-gram of characters, and the characters are X, Z, R, Q, or XKCD, right? Those are supposed to be a random set of characters. And probably nothing has XKCD in it. Now there's a comic, but when they started the name of the comic, he picked those random characters because he thought no one else would ever use those. Okay, so I'll just get back on topic. Thank you, Switch. Okay, so this would probably be fairly wasteful. We don't want to generate the random rows. We're going to think of this from the perspective of the data. Every time we see something in the set, we want to generate something random about that and process it that way. So kind of flip this around somehow. Okay, so what we're going to think of doing is we want a hash function from this domain. All right, let me make my notation more consistent. Some hash function from the domain that our set is in. So our sets are subsets of this. I got that backwards. Okay. So our sets are a subset of this domain. So for every element in the set, I want to hash it into its row location. So I want to, for every element, I want to randomly hash it into one of its rows. Now I could have collisions if I do this, right? This could be a problem. Well, so instead of doing that, why don't I instead hash it to a random value between 0 and 1. So it's some random value between 0 and 1. So, so I'm going to use this random hash function. Actually, okay, there's some, you're going to do this at low level details, but you don't actually need to do this. Let me take this back. Okay, so I'm going to go, if I do it to n, now there's probably going to be some collisions, but as long as they're not the top thing colliding, it's going to be okay. Instead, I could do something like 100n or n log n. Like I don't expect, like from the coupon collectors, say if I did 100 n log n, that I don't expect to have any collisions, for instance, right? So I'm going to create a random hash function here, right? And so then something is the minimum value if for everything in the set I just keep the minimum, right? So now I can think of for every entry in the matrix in the vector I'm going to have the jth entry. Each of those is going to get its own hash function, and so then my algorithm is going to look like this. So let me write out the algorithm, the code for this. For all the elements in the set, okay, so then for all of my j equals 1 to k, so this is all the entries, I don't think I spelled that right, in the vector. Okay, so for all the entries in the vector, then I'm going to say if my hash function j, the jth hash function I have, so assume I have k of these hash functions of x, is less than vj, then I'm going to set vj is equal to the hash j of x. Okay, and so I'll start with the vector of v1 equals essentially infinity, v2, so some very large number, essentially. Okay, so this is my vector, and then if I see something that's, in this case, smaller, so I'll order things. So when I hash to something smaller, then that's the smallest thing I've seen so far. It's hashed to some value between 1 and 100 n log n, right? And so I hash to some value. And so then if it's the smallest thing I've seen so far, I keep track of that. Right? And so I can also store, this is the vector value. I can store, there's some slightly different ways you can implement this. If you notice up here, I kept the actual element of the row. So this would be the value, keeping the value x instead here. But I've kept the ordering. In this way, I've just kept the ordering. If I want to keep the value x, then to set the vth enter, I could rename this variable and have this be like this be yj, and then vj is equal to x, right? So I can do that instead if you want to match the notation I had earlier. But these will effectively be the same thing. They'll only be the same value if they hash together. Okay, so this is a much cleaner algorithm. I can just use this hash function to just maintain the smallest thing I've hashed to so far. Okay, and so if you've noticed, I did this thing where I looped over so I'm looping over all of the hash. So I'm looping over all the hash functions here instead of here. I could have swapped these two for loops and it would have worked the same, right? Do you think it'd be better to swap the two for loops? Or does anyone have any questions about how this works? Right? Do you want me to go through a small example? Yeah.
So, I'm just trying to see if I understand it. So you're basically like, you take one hash function, you apply it to everything in the set, and then you find out, you store the minimum thing that got hashed, and then that's like entry one. And then you go to your next hash function, and then apply it. Is that like what's it?
Except I'm reading, for every element, I go through all the hash functions in
Okay,
internal.
well you could do it the other way.
Yeah, so I can swap them, but before I talk about that, just are there questions about how this algorithm works maybe I'll go through a small example, right? So let's just look at one set, S. So let's look at a set here. This is going to have in it, the elements are going to be, let's call them A and B and C, okay? And so then I'm going to hash function is going to go that, I'll just define it on these values. H of A, so I'll have two hash functions. H of A is going to be defined this way. Let me write it like this. So I'll have H of 1 and H of 2, and I'll have A, B, and C. And so this will be the definition of these hash functions. For H1, it's going to map A to 7, and H2 will map A to 2. HB is going to map B to 3, and this one is going to map B to 10, and this is going to map C to 22, and H2 will map C to 1. Okay? So now I'm going to start with my vector has values infinity, infinity, and I'm going to go and I'm going to process, so this would be my vector here. I'm going to process A with this hash function with hash 1, and it's going to give me a value 7, which is less than infinity. So I'm going to fill this in here. So this is after I processed A. And hash function 2 will give it a value 2, which is less than infinity. So I'm going to get a value here. Okay, now I'm going to process B. Hash function 1 is going to map it to 3, which is less than 7. So I'm going to replace 7 with 3. I'm doing the version with the blue, not this red version that matches the new version. Okay, and then for B, it's going to map to 10 for H2, which is larger than 2, so I keep 2. Right, then I'm going to do C. C is going to map to 22, it's larger than 3, so I ignore it. So I keep 3, and C is larger, is going to map to 1, which is less than 2, so I'm going to keep that. Right, so my vector in the end is going to be 3, 1. This will be my representation.
Of the whole set, right?
Of the whole set, yeah. Yeah.
And if you had multiple sets, you just keep doing this for each set, replacing whatever was in.
Well, each set's going to be a different vector.
Okay.
So this will be the vector representation of the set S. If I had another set, S prime or S2, it's going to give me a different vector. So remember, I'm mapping sets to vectors, and these vectors will work within this LSH scheme we'll talk about on Wednesday.
And the hash values are determined randomly.
Yeah, so the hash values were determined randomly. Remember how these random hash functions worked, in that the hash function itself is deterministic, but the mapping is random. So think of you're picking a random seed which map these, and so instead of these values A, B, and C, these could be strings or something that you're mapping into these integers. Okay. All right, so I do this for each set, and if I had a bunch of sets, yeah, I'm going to get a bunch of vectors out. Each set will get a new vector. This is to convert from a single set into a single vector representation. So, okay, so why would I, so now if I swap these two lines, if I swap the two for loops, right, then it's going to give the same result. I'm just going to, I'll first process this column, and then I'll process this column, instead of first processing this row, and then this row, and then this row. It's generally kind of, it's usually better for very big sets to think of processing it in this way. So why would this be? So typically, what you do is you would think that even though, we need something like 1,000 or 10,000 of these different hash functions, those are going to stay in memory of the computer. Whereas the sets are things that we're reading, maybe reading as they come in, or we're reading them off of disk. Right? So these are going to be big objects that we're compressing, or we're scanning a web page as we're going. We'll talk about crawlers later in the class, and these are kind of these programs that go over the web and read all these web pages. If you do it this way, it only needs to read the web page once. In fact, if you remember, one thing about this, why we use this as a set. The set, this should give the same answer as the same thing as if the set was changed to A, B, A, C, right? If I wrote this as my set instead, meaning I came across these k-grams when I was reading a web page, it should give the same representation as a vector. Right? Because if it sees A again, it's going to go through the hash function, and it's just going to be the same value, so it's not going to be any different. If it's the lowest value, it'll keep it. If it's larger than what's seen before, it won't keep it. Right? So I don't need to go and pre-process things into a set. For every element here, as I go through this step here, if I go through this step, I can do this as I'm scanning over a web page. I can be have a sliding window over the k-grams I'm doing, and immediately throw them into all my hash functions and update my vector. So I can do this as I'm reading over the web page, as I'm reading over an email to process it, right? So that way I don't have to read it over multiple times for each hash function. So this works to create these vector representations kind of on the fly as you're kind of quickly processing this text data. Everything in the k-grams and the set representations kind of fit into this pipeline to immediately calculate these vectors, and this will be kind of the internal representation. There's just a bunch of numbers now representing these web pages or emails. Okay, so just one more thing. Say, just what is the runtime of this? How long would this take to run after this discussion? So it's going to be, so if I have it pre-processed as a set, it's going to be O as the size of the set times K, which is the number of the hash functions. Because for every object, just the 2 for loops, right? So it should be, for every object in the set, you throw it into one of the hash functions. Okay, so if I do, I've used K in 2 ways with k-grams. Let's say it's a g-gram instead. If I'm doing a g-gram over a document with n words in it or n characters, how long is this going to take? So I have a document. Let's say I'm doing a group of g of G words, and I'm doing these G word grams over a document with n words in it. How long is it going to take to create these vectors? Page here, but right. So let's say I've got a document. I'm going to have n words. I'm going to create G word grams. And I'm going to have K hash functions. What is the runtime going to be in terms of the number of words? In terms of these values.
And choose G times K.
And choose G. And choose G times K, which is going to be roughly n to the power G times K. So that'd be pretty slow. Like if G was 3, that's n cubed. It's going to take a long time. I don't think that's going to be right. Yeah.
Is it n times G times K?
N, I'm going to say that one's n times G times K. So that means that for every gram I need to look at, that's also going to be too large. I'm not going to need to spend that much time. What?
N divided by G.
N divided by G. That's going to be too small. Okay, we're getting too, this is too big, and divided by G times K. This is too small. Okay, it's going to be n minus G times K, or you can just ignore the G. Actually, the G doesn't really play, because if I look at a document, so let's just write the alphabet and do it. Right. So if I look at the 3 grams, right. So for each letter, there's one G gram that starts at that location. And then at the end, this one, there's nothing that starts there. So it's actually, I mean, technically n minus G plus 1, okay? But in fact, these are constants, so you ignore them. The big O notation would be n times K. Right, so the size of the G gram is not going to come into play. Right, so this is going to be really fast to read over this. Well, okay. Actually, if I go back, if I'm a little more careful, this is actually going to be the right answer. Because what's going to happen is when I push this into the hash function, this hash function here, it's going to take longer to process something that has more characters or more words in it. Right? So this hash function itself would roughly take O of G time. So this would take longer to run, to process if I had a larger gram. Okay, so actually I will go back and say that this was actually the right answer.
So what if you hit a web page or something that doesn't have any G gram? Like you're doing a 100 gram or something, and it's a tiny little web page that has one word on it. What?
Then you've chosen the wrong value of G, probably. Remember, G is a modeling choice, and you usually get to choose this. So if you're going to be dealing with documents which are very, going to sometimes be empty, then they're probably not very useful documents. So if you ignore them, that's probably okay. So if, there are lots of weird things you could do, like you could combine vectors with different values G, create different vector representations, and then query under both of them and kind of try and combine the results in various ways, or build up, concatenate 2 vectors together that you've built with various G's. And this sort of thing should probably work. But if you're worried about having various things, and often you'll look at one type of data that will fit one category, or you'll use G to be some small value, like 3 or 4. And if you only have one word, then not much you can do. Okay, so I finished a little bit early today. Does anyone have any questions about how this, well, maybe before we leave, just think about how is this locality-sensitive hashing going to work? It's always good before you hear a lecture, before you hear a proof, to try and think how would that work? Why, how could you possibly do this? So think about this locality-sensitive hashing. How would you use these vectors, and in particular, what these hash functions mean to quickly answer these questions? If you have a set of all these documents and you have another one, how would you quickly find all the nearby ones? If you have a bunch of documents, how would you quickly detect if you have duplicates? So you can remove, say, the duplicates from the set, or look for 2 assignments turned in from the class that have basically the same answers. All right. So how would you use this structure to do that? So everyone in here has seen. So everyone in here has done like a basic data structures class, right? Where you've done binary search, right? So if you have binary search, you want to find nearby things, you can sort them, and if you want to do this query, you just use the sorted order along the binary tree, right? And if you want to find 2 similar things, well, if they're in the sorted order, they would have to be right next to each other. But now we don't have a single ordering, so that's going to be the challenge. So we're going to have to think a little bit outside the box, or we can't quite use those ideas anymore. So that's it. So I'll end there today. Thank you. Yeah.
Take the screen.
What?
Click the screen.
Yeah, just click the screen.